We now begin to study power series solutions. We say a function is said to be analytic at a point A if it can be represented as a power series. Centered at A. Another definition. A point x naught is said to be an ordinary point in the differential equation a2 of x y double prime plus a1 of x y prime plus a naught of x y is equal to 0 if both coefficients in the standard form differential equation y double prime plus p of x y prime plus q of x y equals 0 are analytic at x naught. A point that is not ordinary is said to be a singular point. We now want a test on whether a given point is an ordinary point of a differential equation. So we let a2, a1, and a naught all be polynomials. Then x naught is an ordinary point of a2 of x y double prime plus a1 of x y prime plus a naught of x y equal to 0 if and only if a2 of x naught is not 0. And now we come to the big one. The existence theorem. So if x equals x naught is an ordinary point of a differential equation, specifically a second order linear differential equation, then we can always find two linearly independent solutions in the form y equals the infinite sum c sub n x minus x naught to the n. Now, this will converge. So this will always converge at least on some interval absolute value x minus x naught less than r, where r is the distance from x naught to the closest singular point. We will now spend the rest of this lesson looking at two examples. I warn you, finding power series solutions is a very long and tedious process, as we are about to find out. So let's first look at the differential equation. Quantity of x squared plus 1 times y double prime plus x times y prime minus y is equal to 0. All of the coefficients are polynomials. The singular points are where x squared plus 1 is equal to 0, which is plus or minus I. For simplicity of algebra, we will always use x naught equal to 0. This is an ordinary point. So the r is the distance from 0 to the closest singular point. Well, plus or minus I are both equidistant from 0. And the distance is 1. So our interval validity will be the absolute value of x less than 1. So our solution will have the form n equals 0 to infinity cn x to the n. This means that y prime will be a sum from n equals 1 to infinity c sub n times x to the n minus 1, and y double prime will be a sum n equals 2 to infinity c sub n times n minus 1 times x to the n minus 2. What we now need to do is take these three values and plug them in to the differential equation. So we have x squared plus 1 times the sum n equals 2 to infinity c sub n times n minus 1 times x to the n minus 2 plus x times the summation n equals 1 to infinity c sub n x to the n minus 1 minus the summation n equals 0 to infinity of c sub n x to the n, and that whole thing equals 0. Now what we have to do is we have to algebraically simplify this left-hand side. So we're going to have x squared times the sum 2 to infinity c sub n minus 1 x to the n minus 2 plus the summation n equals 2 to infinity of that same thing plus x times the sum 1 to infinity c sub n x to the n minus the sum n equals 0 to infinity c sub n x to the n. Our goal is to try and get all the starting indices to be the same. So I'm going to pull this x squared inside here. That'll give the sum from n equals 2 to infinity of c sub n times n minus 1 times x to the n plus sum n equals 2 to infinity c sub n times n minus 1 x to the n minus 2 plus, now I'm going to pull this x inside the summation. So it's the sum n equals 1 to infinity of c sub n x to the n. I'm sorry, up here that should have been n minus 1, not n. And then we still have the minus summation n equals 0 to infinity c sub n x to the n. So we want to try and get all of these to be starting at the same index. So I want this to stay as 2. This I want to get up to 4, because 4 minus 2 is 2. Then this I want to get up to 2, and this I want to get up to 2. So this first summation is going to stay the same. Now we need to pull out 2 terms from here. So when n is 2, we'll get 2 times 1. So 2c2. Now for the 3 term, we get 3 times 2 is 6. Then x to the 3 minus 2, which is 1. Now that we've pulled out those terms, the summation will now start at 4, as desired. We now need to pull out the n equals 1 term from here. So that'll give us plus c1x. And then plus the summation now starting at 2. And we need to pull out 2 terms from here. So the n equals 0 term will be just c sub 0, then c sub 1x, and then the summation starting at 2 to infinity of c sub n x to the n. We're now going to change this index here so that this becomes just an n, and this becomes n equals 2. I'm also going to move all of my terms that I pulled out of summations to the front. So we will have 6c3x plus 2c2 minus c sub 0 plus summation n equals 2 to infinity of c sub n times n minus 1 x to the n plus summation n equals 2 to infinity. So now I'm shifting this index down by 2. Since we're shifting down by 2, wherever you see an n, it becomes n plus 2. So c sub n plus 2 times n plus 2 times n plus 1 times x to the n. And the other two summations will stay the same. Now that the starting indices are all the same, we can write this as a single summation. So it's the summation n equals 2 to infinity of n times n minus 1 times c sub n plus n plus 2 times n plus 1 c sub n plus 2 plus n times c sub n minus c sub n, and they all have the same x to the n. Now we have to do a little bit of algebraic simplification. So within here, we want to write all of our Cn terms together, and then our Cn plus 2 term. So we'll have n times n minus 1 plus n minus 1, and that whole thing is times Cn, plus n plus 2 times n plus 1, and that is times Cn plus 2, and it's still all times x to the n. Now summation n equals 2 to infinity. When you expand this out, we'll have n squared minus n plus n, which is 0, so it's n squared minus 1. So it becomes n plus 1 times n minus 1 c sub n plus n plus 2 times n plus 1 c sub n plus 2, all times x to the n. And this whole thing has to be 0. So we're going to look at two terms individually. We look at this, and we'll look at this. So if 6c3 of x is equal to 0, then we'd have C3 has to be 0. Right, we know this because we're doing coefficient comparison. 2C2 minus C0 has to be 0, and so C2 would have to be a half of C0. Now we look at n plus 1 times n minus 1, C sub n, plus n plus 2 times n plus 1, C sub n plus 2. This has to be 0. This means that C sub n plus 2 is equal to negative n minus 1 over n plus 2 C sub n. We can also distribute that negative through and write this as 1 minus n over n plus 2 C sub n. Now this is called a recurrence relation. Each C sub n plus 2 depends on the C sub n term. Now since n is starting at 2, we'll start there. So n equals 2 will give us C sub 4. By the relation, it would have to be negative a quarter C sub 2. But C sub 2 is a half C naught. So this would become negative 1 over 2 times 4 C sub 0 C naught, which can be written as negative 1 over 2 squared times 2 factorial. C sub 0. The reasoning for writing it like this will make sense very shortly. Now let's look at the n equals 3 term. This will give us C sub 5. So by the recurrence relation, this has to be negative 2/5 C sub 3, but C sub 3 is 0. N equals 4 gives us C sub 6. So this has to be negative 3 over 6 C sub 4. But C sub 4 was up here. So it's 3 times 1 over 2 squared times 2 times 6. And this equals, C0, which equals 3 times 1 over 2 cubed times 3 factorial, C sub 0. For n equals 5, C sub 7 is negative 4/7 C sub 5, but C sub 5 was found to be 0, so this is 0. We're already starting to see now the emergence of a pattern. All of the odd C's are going to be 0. So let's look at the n equals 6 term. This will give us c sub 8 is equal to negative 5 over 8. C sub 6, which was given above. So we get negative 5 times 3 times 1 over 2 cubed times 3 factorial times 8. But 8 is 2 times 4. So we now have negative 5 times 3 times 1 over 2 to the 4th times 4 factorial, c sub 0. C sub 9 is going to be the n equals 7 term, and you'll easily see that that is 0. You want to keep doing this until you can see a pattern. So the general solution, so the form c0 plus c1x plus c2x squared plus c3x cubed plus so on and so forth. So this is going to equal c sub 0 times, remember, c0, c2, c4, so on and so forth can all be written in terms of this c sub 0 term. So what do we get? We have 1 plus 1/2 x squared minus 1 over 2 squared times 2 factorial x to the 4th plus 3 times 1 over 2 cubed times 3 factorial x to the 6th plus 5 times 3 times 1 over 2 to the 4th times 4 factorial x to the 8th plus so on and so forth, plus simply c sub 1x, because all of these other odd c's are going to be 0. Now I'm going to make a note that I can write this as 3 double factorial, and I can write this as 5 double factorial, and so on and so forth. In general, n double factorial is n times n minus 2 times n minus 4, so on and so forth, and take it down to times 1. Or times 0. No, not times 0. Or just times 1. So what this is saying is a double factorial acts just like a factorial, except you skip terms. So it's the product of every other integer. My goal now is to try and write this as a power series, if possible. So this would equal c sub 0, 1 plus 1/2 x squared plus, now let's look at a summation. It's going to start at 2 and go to infinity, right? Because this is the 0 term, this is the 1 term, here's the 2 term. We notice that these are alternating. Up here, I'm sorry, this should have been a minus. The signs are alternating, so it's going to be a negative 1. So this is 0, 1, this is an even term, odd, even. So all of the even terms are negative, all of the odd terms are positive, so this should be an n minus 1 or an n plus 1. It doesn't matter which one. We want to look here. Well, our n, or all the exponents are evens. So this is 0, 2, 4. So it looks like the exponent of x is going to be 2 times n. So for here, the n is 2, and this is 1. This is 3, and we get 3 times 1. 4, we have 5 times 3 times 1. The general pattern is 2n minus 3 double factorial. All over 2 to the n times n factorial x to the 2n, and then plus c1 of x. I'm sorry, c sub 1 times x. This is our general solution. And we can't forget the interval of validity is absolute value of x less than 1. Like I said, it's not particularly difficult. It's just extremely tedious because there is a lot of algebra involved in this technique. The next example we're going to look at will be an example where the coefficients are not all necessarily polynomials. We now look at the differential equation, y double prime plus cosine of x and y is equal to 0. Now again, we notice that x not equals 0 is an ordinary point. We also notice that there are no singular points. So that would give us r is infinite. So our solution will be of the form summation c, so then x to the n as before, so y prime and y double prime. We will also take note that cosine of x can be represented by the series n equals 0 to infinity minus 1 to the n x to the 2n over 2n factorial. This you should have studied in Calculus 2. We will now replace all of the terms in the differential equation by these. So we'll get summation n equals 2 to infinity cn n minus 1 x to the n minus 2 plus the summation n equals 0 to infinity minus 1 to the n x to the 2n over 2n factorial times the summation n equals 0 to infinity c sub n x to the n. And remember, this has to equal 0. Now, unlike in the previous example, it's going to be really difficult to try and keep everything in summation notation, because finding a formula for the product of sums is extremely difficult. So what we're going to do for this example is just write out the first several terms of each summation. So for this first one, we'll get 2c2 plus 6c3x plus 12c4x squared plus 20c sub 5x cubed plus so on and so forth plus 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus so on and so forth times c sub 0 plus c1x plus c2x squared plus c3x cubed plus so on and so forth. So we're going to group all terms together, so that's our constants, our x terms, our x squared terms, our x cubed terms, and so on and so forth. And remember now, this whole thing has to equal 0. So now we do coefficient comparison. 2c2 plus c0 has to be 0. And so c2 is negative a half c0. 6c3 plus c1 has to be 0. So c3 is negative a sixth c1. 12c4 plus c2 minus a half c0 has to be 0. And so we'll get that c4 has to be negative a 12th c0. And then 20c to the c5 plus c3 minus a half c1 has to be 0. And we get that c5 is a 30th c1. And I'm sorry, c4 should not be negative. With this, we will write a general solution of the form c0 times 1 minus a half x squared plus a 12x to the 4th minus yada 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 plus c1 times the quantity x minus 1/6 x cubed plus a 30th x to the 5th minus yada yada yada, and the interval of validity is, of course, all real numbers. And again, it's really difficult to try and write this in a summation form, so we're going to leave it in this form. That concludes this lesson. I hope you've learned something, and we will see you in the next one.